Imagine waking to a planet that still has mountains, clouds, deserts, forests, and sunlight, but no shorelines at all. No Atlantic breaking against Europe, no Pacific breathing against Asia, no Arctic ice floating over dark water. Only a vast, exposed wound where the oceans used to be, a second face of Earth suddenly laid bare. Abyssal plains, drowned mountain chains, trenches deeper than Everest is tall, and continental shelves stretching outward like ghost coasts from a forgotten world. It would be one of the strangest sights the planet could ever produce. Ports would hang above emptiness, river mouths would lead nowhere, salt flats would spread across former seabeds. The great blue mirror that softens the sky, stores heat, feeds clouds, and connects every coast to every other coast would be gone. And with it, the rhythm of tides, the moderation of climate, the immense living web of marine life, and much of the quiet stability that makes Earth feel familiar. Science does not offer any realistic mechanism by which all of Earth's oceans could simply vanish overnight. But science does tell us, in extraordinary detail, what the oceans do. We know how they move heat around the globe, how they drive evaporation and rainfall, how they shape coastlines, how they feed food webs, how they store carbon, and how they hide most of our planet's habitable space beneath their surface. We have mapped enough of the seafloor, studied enough of climate, and learned enough about Earth systems to ask a serious question wrapped inside an impossible one. What if Earth's oceans disappeared? Not as fantasy for its own sake, but as a way of understanding what the oceans really are. Not scenery, not empty blue space on a map, but one of the central engines of the world we know. By removing them in thought, we can see more clearly how deeply they are woven into weather, geology, evolution, civilization, and even the possibility of us. That is what makes this thought experiment worth following. Even when the premise is extreme, the consequences can be traced through real processes, real landscapes, and real dependencies that already exist all around us. Because once the water is gone, familiar geography stops making sense, and Earth begins to reveal how much of its balance was built on something most of us take for granted. So tonight, we are going to travel across a dry Earth, step by step, from the first impossible silence of empty ocean basins to the long unraveling of climate, life, and the human world. And before we begin, take a moment to like the video, subscribe if you enjoy these long journeys, and tell me in the comments where in the world you're listening from. Now, dim the lights, settle in, and take a slow, deep breath. Let the noise of the modern world drift a little farther away, and together, let us step onto the floor of an ocean that no longer exists. Beneath that vanished sea, the first sensation would not be motion, but stillness. An ocean floor is never meant to be seen in open air. It is shaped under pressure, under darkness, under miles of water that soften every horizon and mute every line. Yet now it lies exposed from coast to trench, a planetary interior turned outward, a hidden geography revealed in a single impossible instant. The seabed stretches away in all directions, cold, immense, and silent, with the strange dignity of a world that spent billions of years concealed and was never designed for the human eye. If the oceans disappeared all at once, the change would be greater than any flood, any earthquake, any eruption, any shift of climate our species has ever known. Sea level would not simply fall, it would collapse. Every coastline on Earth would be redrawn in a moment so abrupt that the old maps would become historical artifacts, before a person could finish unfolding one. The familiar edge between land and water, the line that gave shape to continents, nations,
Ports, beaches, wetlands, harbors, estuaries, and deltas would vanish as an organizing principle of the surface. What remains would be larger, harsher, and far more confusing than the simple idea of dry land suggests. The first places to appear would be the continental shelves, those broad, shallow margins that surround the continents like submerged steps. Today, they are hidden under relatively modest depths of seawater. They hold fisheries, reefs, kelp forests, shipping lanes, and much of the busiest biological activity in the marine world. In this dry earth, they would emerge almost immediately as enormous plains attached to the continents, extending them outward by distances that, in some regions, would feel astonishing. What was once the coast of France, of China, of Argentina, of eastern North America, would suddenly be far inland from the new edge of the world. These newborn plains would not resemble the smooth, sandy bottoms imagined by those who have only looked at coastlines from above. Some would be muddy, scarred by channels cut by ancient rivers when ice ages lowered the sea. Some would be patterned by sand ridges, reefs, shoals, and the remnants of drowned landscapes. Others would bear the geometry of tidal flats and submarine dunes, or the broken texture of shell beds, sediment waves, and ancient glacial deposits. In a few places, human structures would still sit on the old coast, now marooned above vast open distances, while pipelines, drilling platforms, wind farms, and wrecked vessels stood stranded in the middle of what had become a landlocked emptiness. Farther out, beyond the shelf break, the planet would change character again. The surface would tilt downward into the continental slope, the first true descent toward the deep sea. Underwater, that slope is a boundary of pressure, current, and darkness. In air, it would become something closer to a continental escarpment, a long, uneven fall into the exposed basins of the former oceans. From some points, it would look like a distant range of cliffs. From others, it would resemble a staircase on a scale beyond architecture. Submarine canyons, once carved by sediment-laden flows and hidden in darkness, would open as giant wounds in the margin, complex and branching, each one larger than valleys known by name on land. The world would then begin to reveal its second face in earnest. The deep ocean floor is not flat in the simple sense. Much of it is broad and level compared with mountain belts, but it is still a terrain, a place of rises, trenches, scarps, volcanic cones, fracture zones, sediment plains, and ridges thousands of miles long. The abyssal plains, those dark reaches that, under modern seas, lie beneath 4, 5, sometimes 6 kilometers of water, would appear as vast mineral deserts, broader than most nations. They are among the smoothest surfaces on Earth when submerged, draped over long ages by settling particles. But in open air, they would not feel smooth. They would feel deadened, expansive, and strangely unfinished, like silence given form. Crossing them, one would encounter seamounts, underwater volcanoes that never broke the sea surface, or once did and then sank. Some are solitary, some occur in chains, the track of tectonic motion over mantle hotspots. In a world without oceans,
They would stand as isolated mountains in the middle of former basins, abrupt and lonely, with flanks built from lava and capped, in some cases, by flat tops where ancient islands were planed by waves long before sinking beneath the sea. Those flat-topped mountains, called guillotes, are among the most haunting clues that the ocean floor has a history as dramatic as any continent. Their very shape remembers a lost shoreline, and now, exposed again, they would rise from the deep like monuments to time itself. Long before a person reached the true center of an emptied ocean, another giant feature would begin to dominate the horizon: the mid-ocean ridge. This is one of the greatest structures on Earth, a volcanic mountain system that wraps around the planet for tens of thousands of kilometers, marking places where tectonic plates pull apart and new oceanic crust is created. Hidden beneath seawater, it is easy to forget that the planet wears this wound continuously. In the dry basins, it would emerge as a global spine, rugged in some stretches, broad in others, cut by faults, segmented by fracture zones, and in places split by rift valleys. It would be less like a single mountain chain than a whole world of fractured volcanic highlands, the architecture of plate tectonics suddenly made visible. If the vanished sea had once covered the Atlantic, you could imagine standing on the dry floor west of Africa and seeing, far in the distance, the broad rise of the mid-Atlantic ridge. Where hydrothermal vents once mineralized the darkness, there would be fields of sulfides and altered rock, relics of a world where seawater circulated through newly formed crust and returned in superheated plumes. Those vents, among the most extraordinary habitats on the modern Earth, would no longer vent into water. Their chemistry, their ecology, and their strange local climates would collapse almost instantly. Yet their mineral remains would still mark the places where the crust had once exchanged heat and elements with the ocean above. Then there are the trenches. Under modern oceans, the deepest parts of the sea are almost beyond intuition. We know their numbers. We know that some descend deeper than 11 kilometers below sea level. We send instruments there. We map them with sound. But we do not carry an ordinary mental picture of what such depth means, because water softens it. Seen directly, an exposed trench would be less like a canyon and more like a continental scale rupture, its walls descending into shadow, its floor so far below the surrounding basin that atmosphere itself might begin to feel different at the bottom.
The Mariana Trench, the Tonga Trench, the Peru-Chile Trench, and others like them would cease to be abstract measurements and become the deepest open scars on the surface of the planet. At first glance, one might imagine these exposed basins as immediately accessible. In reality, they would be among the most hostile landscapes on Earth. Much of the former seafloor is composed of fine sediments, biological debris, clays, silts, oozes made from shells and skeletons, volcanic ash, and particles that drifted down through water over immense spans of time. Deprived of pressure and submerged stability, many of these materials would crack, compact, slump, or crumble. Some areas would dry into crusts, others would split into plates. Some would release trapped gases or fluids. Some would simply become enormous plains of unstable sediment, difficult to cross and difficult even to read. The ocean floor would not become welcoming terrain. It would become a new category of desert. The immediate transformation of Earth's appearance from orbit would be almost as startling as the change at ground level. The blue planet would no longer be blue in the way every astronaut has described it.
The reflective skin of ocean water that now dominates the view of Earth from space would be replaced by an irregular map of exposed shelves, pale, salt-rich flats, darker abyssal basins, and cloud systems beginning to lose the source that sustains them. Continents would appear wider. The boundaries between land and sea would no longer gleam. Instead, the planet would take on a starker, more mineral character, with a broken, exposed surface that made Earth look older, harsher, and perhaps more alien than the worlds we usually call alien. On the ground, however, people would not first encounter abyssal plains and trenches. They would encounter the death of the coast. A city like New York, Shanghai, Lagos, Rio de Janeiro, or Sydney is not merely near the sea. It is built in conversation with it. Harbors,
trade routes, fisheries, weather patterns, waterfront industries, and cultural identities all assume that the ocean is still there, just beyond the quay or estuary or beach. Remove that water in an instant, and the city does not simply become inland, it becomes geographically absurd. Ferries would sit on mud or rock, piers would extend over emptiness, container terminals would overlook an exposed landscape where ships could never sail again. In some places, old coastlines would end in cliffs, though not always vertical ones. The difference in height between land and newly exposed shelf might be gentle where the shelf is broad and shallow, but where coasts descend quickly into deeper water, the loss of the sea would reveal sudden drops and steep margins. River mouths would be transformed most dramatically. Estuaries, now places where fresh and salt water mingle, would become elongated valleys leading into barren shelf plains. Delta systems, such as those of the Nile, Ganges, Brahmaputra, or Mississippi, would no longer spread into the sea. Their channels would wander into giant dry spaces that had once been marine. Sediment would no longer settle into coastal waters. It would be delivered into exposed basins or trapped in newly formed inland depressions. The psychological shock of this should not be underestimated. Human beings know where the sea is without thinking. It lies at the edge of maps, at the horizon of memory, at the source of weather, food, travel, fear, and beauty. Remove it, and even those far from the coast would feel a rupture in orientation. The word west or east carries different emotional weight in a world shaped by ocean basins. Maritime climates moderate seasons. Monsoons depend on temperature contrasts involving sea and land. Storms gather over warm water. Ocean currents distribute heat toward poles and coasts. A world without oceans is therefore not merely a world missing scenery. It is a world whose deepest patterns of familiarity have been cut loose from their source. Yet, for a brief moment after the impossible event, the sky above this transformed Earth might still look deceptively ordinary. Clouds would still exist. Air masses would still move. Moisture, already present in the atmosphere, would still circulate. Some rain would still fall. Rivers would still flow from the water already in their channels, in lakes, in groundwater, in snowfields and glaciers. For a short while, the planet might seem to be hesitating, as though the full meaning of what had happened had not reached the atmosphere yet. This pause matters because it reveals something profound about Earth systems. Even when one of the largest is removed, the consequences unfold through connected processes, not all at once. Still, the first true atmospheric change would already be underway. Oceans do not simply store water. They are the dominant evaporating surface of the planet. The modern water cycle depends overwhelmingly on ocean evaporation,
which transfers water vapor into the atmosphere, feeds cloud formation, and later returns moisture to land and sea as precipitation. With the ocean surface gone, that exchange would be severed at once. The air would not empty of moisture instantly, but the replenishment would stop. Existing weather would become a dwindling inheritance, a last circulation of borrowed vapor from a vanished sea. There is another subtle loss as well, and it would change how the planet feels long before all the later consequences become obvious. Water has enormous heat capacity. It absorbs energy slowly and releases it slowly, acting as a global buffer. This is one reason coastal climates are milder than continental interiors. It is one reason the daily and seasonal rhythms of temperature are not more extreme than they are. With the oceans gone, huge regions of the surface would no longer act as thermal reservoirs. Instead,
Exposed sediments and rock would heat and cool far more quickly. The full climate effects would take time to unfold, but the moderation itself would begin disappearing from the first day. The drying seabed would also begin to alter the chemistry and texture of the air near the ground. Marine sediments contain salts, organic matter, microbes, and minerals that have accumulated under unique conditions. Expose them suddenly, and they do not simply become ordinary soil. Some would crack and crust, some would release odors of sulfur or decay, some would turn to dust when disturbed, some might remain tacky or unstable for a time, depending on the retained moisture in sediments and the local temperature. In enclosed former basins and sheltered shelves, stagnant air could gather over these new surfaces, carrying unfamiliar aerosols and particulate matter into regions that had once known only sea spray. One of the strangest sights on this dry earth would be the stranded architecture of human activity offshore. Oil platforms that once rose from the sea would now stand over empty depth, linked to nothing. Undersea cables, designed to rest invisibly on the ocean floor or be buried beneath sediments, would emerge along the shelves and slopes like exposed nerves connecting continents across open basins. Shipwrecks from every century, once hidden in darkness and sediment, would begin to appear in astonishing numbers near old trade routes, anchorages, and coasts. The history of commerce, war, migration, and disaster would be exposed physically, scattered across the new plains of the former sea. Closer to the old shore, ecological collapse would be immediate and intimate. Tidal flats, salt marshes, mangroves, seagrass meadows, coral reefs, kelp forests, estuaries, lagoons, and shallow coastal nurseries are among the richest habitats on Earth, and almost all of them depend on the simple, continued presence of shallow seawater. Without it, they do not degrade gradually over centuries. They lose their medium. Coral reefs would dry, bleach, and die under open air and sunlight. Kelp forests would collapse into mats and then rot. Tidal animals adapted to hours of exposure, not perpetual exposure, would perish quickly. The first biological silence would not begin in the deepest sea. It would begin around the very coasts that today teem with life. Fish would be among the most visibly affected, but even that word hides enormous differences. Pelagic species of the open ocean, coastal schooling fish, deep sea forms, reef fish, migratory species, sharks, rays, cephalopods, and larval stages drifting in the plankton all depend on three-dimensional water for movement, feeding, and breathing. An instant removal of the ocean would leave no path for adaptation. Large animals would be stranded or crushed by the disappearance of buoyancy. Small animals would desiccate. Many would die in dense masses across shelves and basins, especially in shallower regions where currents once concentrated life.
There would be no orderly retreat to deeper water, because deeper water would no longer exist. The entire volume of the habitat would be gone. Marine mammals would present a particularly heartbreaking image, though the reality would unfold differently in different places. Whales, dolphins, and porpoises depend on buoyancy not just for movement, but for the support of their massive bodies. Out of water, large whales can suffer severe stress under their own weight. On a suddenly emptied ocean floor, their fate would be swift and overwhelming. Seals, sea lions, and some coastal mammals could survive longer on land than whales, but the loss of marine feeding grounds would still collapse the systems that sustain them. Seabirds, too, would be thrown into chaos. Their nesting grounds might remain, but their foraging world would disappear in a day. Much of the marine biosphere, however, is too small to picture directly, and this makes its loss even easier to underestimate.
The ocean is not mostly whales and fish. It is largely microscopic life, drifting life, suspended life, microbial communities, and the tiny engines of photosynthesis that help regulate the atmosphere itself. Phytoplankton, zooplankton, bacteria, archaea, and the endless food webs built upon them are foundational to marine systems. Remove the water column, and you erase not only visible organisms, but the medium in which these communities interact, reproduce, migrate, and transform carbon and nutrients. The silence of the sea would therefore be biochemical as well as acoustic, a collapse in processes too vast and too small to perceive without scientific language. The deep sea is often imagined as remote from the rest of Earth, but its apparent remoteness is misleading. It participates in global nutrient cycles. It stores carbon in sediments and deep waters. It is tied to surface productivity through the slow rain of organic matter from above. It hosts ecosystems based on chemosynthesis in places where sunlight never reaches. The disappearance of the ocean would therefore erase not only what humanity knows well, but much of what humanity has scarcely begun to study. Entire branches of evolutionary history, entire metabolisms, entire ecological experiments would vanish from active existence before most people even understood that they had been there. And yet, because this is a thought experiment rooted in real science, it is worth asking what would remain, if anything, on these sudden marine landscapes. Some organisms from intertidal zones can tolerate periods of exposure. Some microbes could persist in damp sediments, trapped brines, or chemically unusual niches. Some deep subsurface communities, already living within rocks and sediments beneath the sea floor, might endure as long as liquid water and chemical gradients persisted below ground. In other words, the marine biosphere would not become literally zero in every microscopic crevice at once. But as a functioning planetary ocean system, it would be broken beyond recognition immediately. What makes all this especially unsettling is that the ocean floor itself carries evidence of time on scales human life rarely feels. Sediments settle there, grain by grain. Skeletons accumulate. Volcanic crust forms and moves outward from ridges over millions of years. Ocean basins open and close over the age of continents. Trenches consume crust older than our species by lengths of time that feel almost mythic. In our hypothetical dry Earth, those durations would suddenly be visible as layers, patterns, scars, and structures. The vanished ocean would reveal not only a lost present, but an archive of the planet's deepest rhythms. To stand there would be to stand inside geological memory. Some former basins would be more dramatic than others. The Atlantic, relatively narrow and framed by opposing continents,
would feel like an exposed global corridor. Shelves, slopes, abyssal plains, then the mid-Atlantic ridge, then plains and slopes rising again toward another continent. The Pacific, vast beyond intuitive scale, and edged by trenches, volcanic arcs, and complex margins, would become a continent-sized emptiness, a place where the horizon itself might fail to communicate the true magnitude of the exposed floor. The Indian Ocean, the Southern Ocean margins, marginal seas like the South China Sea or Mediterranean, and enclosed basins like the Black Sea, would each reveal different architectures shaped by their own tectonic and climatic histories. The Mediterranean is an especially haunting example because it already holds in its geology a memory of extreme desiccation. Several million years ago, during the Messinian salinity crisis, the connection between the Mediterranean and the Atlantic was severely restricted, and large parts of the basin appear to have undergone dramatic drying and salt deposition. The exact details remain complex and are still studied,
but the basic lesson matters. When a marine basin loses connection to the ocean and evaporation exceeds inflow, the result can be catastrophic drying and enormous salt deposits. Our scenario is far more extreme and global, but that ancient episode offers a real hint of how strange the exposed remains of a vanished sea can be. There would also be moments of deceptive beauty. Former lagoons might become mirror-like salt pans. Exposed reefs could stand as limestone labyrinths under low sun. The shelves at dawn might glow pale gold or silver. The ridges and fracture zones in the dry abyss could cast long, elegant shadows. Some areas might look sculpted, serene, almost inviting from a distance. But this beauty would be inseparable from absence. Everywhere, the shapes would say the same thing in different languages of rock and sediment. Water was here, and now it is not. The earth would look not newly made, but deprived. At the poles, the disappearance of the oceans would produce another category of strangeness. Today, the Arctic is defined not by land at its center, but by an ocean capped seasonally by floating sea ice. Remove the water, and the entire geometry of the region changes. The floating ice itself could not remain as it was because sea ice depends on seawater beneath it. Some of it would collapse, fracture, or ground onto newly exposed seafloor and shelf. The central Arctic basin would emerge as a cold depression ringed by continents, while the familiar idea of a frozen ocean would be replaced by an exposed polar landscape no human culture has ever known. Around Antarctica, floating ice shelves would lose the water beneath that supports them, abruptly altering their stability, even though the great grounded ice sheet on land would still remain longer as stored fresh water. The end of the tide would also leave a mark deeper than it first appears. Tides are so ordinary that many people think of them as something relevant to harbors and beaches. In reality, they are a regular planetary motion, a daily expression of gravity written into coastlines. With no oceans, there would be no tides in their familiar form, no advancing and retreating shoreline, no intertidal rhythm, no moon-drawn breathing of bays and estuaries. Entire suites of organisms depend on that pulse. Entire human traditions are timed to it. Its disappearance would remove one of the oldest recurring signals in the lived experience of coastal Earth. The moon would still rise, its pull would still exist, but one clear sign of that pull in daily life would be erased. There is also the matter of sound. The modern coast is rarely quiet. Even on calm days, there is surf, wash, spray, tidal movement, the persistent friction of water on land.
Offshore, there is the low roar of waves, the crash of storms, the creak of ice, the calls of seabirds, the hidden acoustic world of marine mammals and fish. A dry Earth would lose that continuous soundtrack almost immediately. Beaches would not hiss under retreating water because there would be no retreating water. Harbors would not slap against hulls. Cliffs would no longer hear swells arrive from a distant storm. In many places, the silence might feel more shocking than the sight, because the sea is as audible as it is visible. The absence of waves would make the planet feel not only emptied, but muted, as though one of its oldest voices had been switched off. For the marine organisms of the deep, the disappearance of pressure would be as fatal as the disappearance of water itself. Creatures living kilometers below the surface are adapted not simply to darkness and cold, but to immense hydrostatic pressure. Their biochemistry, body structure, membranes, enzymes, and buoyancy are tuned to conditions that surface life never experiences. Bring them upward through open air, and the problem is not only desiccation, it is the total collapse of the environment in which their bodies make sense.
Many of the most extraordinary deep-sea forms, from gelatinous predators to pressure-adapted fish and invertebrates, would not even be recognizable for long outside their native world. The public imagination often turns the deep sea into fantasy, yet here, the reality is most fragile. The deeper the habitat, the narrower the range of conditions under which life there can continue. Bioluminescence, one of the most beautiful signatures of the living ocean, would vanish with startling speed. In the modern sea, light is not confined to the surface. It is made by organisms in darkness, used for hunting, defense, mating, camouflage, misdirection, and communication. It flickers in plankton, shines in jellies, glows in siphonophores, pulses in deep fish, and appears as cold fire in water that sunlight never reaches. On a dry planet, this hidden lantern world would be extinguished almost at once. It is a small detail compared with global climate or tectonics, yet it captures something essential about the loss. The ocean is not only vast, it is internally expressive. It holds living forms of light, motion, chemistry, and relation that have no true counterpart on land. Their disappearance would dim the world in a way no orbiting camera could record. As the newly exposed seafloor met the atmosphere, chemical changes would begin immediately. Sediments and minerals long sealed beneath seawater would be oxidized. Sulfides formed in oxygen-poor environments could react with air. Carbonates, clays, evaporites, volcanic glass, and organic-rich muds would all begin responding to conditions they had not experienced in ages, or, in some cases, had never experienced at all. Some reactions would be subtle, others locally dramatic. The exact behavior would vary from basin to basin, depending on composition, temperature, retained moisture, and microbial activity. Scientists would rush to sample these surfaces because they would offer a once impossible natural experiment in geochemistry. Yet the same exposure that makes them scientifically valuable would also ensure that many original states were lost quickly. The revealed archive would begin weathering the moment it opened. In regions where methane hydrates exist within marine sediments, the removal of seawater and pressure could pose another uncertain and potentially significant consequence. Methane hydrates are ice-like compounds in which methane is trapped within water molecules under particular conditions of pressure and temperature, often in continental margin sediments or beneath permafrost-associated zones. Their stability is sensitive. Without overlying seawater,
some deposits might destabilize, though timing and scale would depend on local geology and thermal conditions. This is one of those places where careful science must stay modest. Not every hydrate-bearing sediment would suddenly erupt, and much would depend on depth, burial, and retained cold. But the point remains, the former seabed would not merely dry. In some areas, it could begin changing from within, releasing gases or fluids that had once been held in quiet balance beneath the weight of the sea. The modern human world is knitted together by roots that assume buoyancy and waterborne efficiency. Most global trade by volume moves by sea. Bulk cargoes, fuel, grain, manufactured goods, and the tempo of modern life depend on ships crossing water that can carry immense weight far more cheaply than land transport. On a dry Earth, those routes would not be interrupted in the ordinary sense. They would be abolished. The narrowness of straits, the position of canals, the importance of ports, the strategic meaning of choke points like Malacca, Suez, Hormuz, Panama, Gibraltar, or Bab el-Mandeb would vanish as maritime facts and be replaced by a new, rugged geography of slopes, shelves, and exposed basins. Even before the larger climate crisis fully unfolded,
Civilization would face the practical truth that the planet's great circulatory system of trade had been built upon water no road could easily replace. The history of life on land would also look different in the light of this disappearance. Many people think of oceans and continents as separate theaters, one marine and one terrestrial. In reality, land life has always been shaped by the nearby sea, even when the sea is far away. Marine evaporation feeds continental rain. Oceanic moderation tempers seasonal extremes. Nutrients move through upwelling and atmospheric transport. Many migrations, breeding cycles, and evolutionary pressures are linked to shorelines, estuaries, and shallow seas. To watch the oceans vanish would therefore be to watch the background conditions of terrestrial life begin slipping out of alignment. Forests would not die instantly. Grasslands would not disappear overnight. But from the first day, the terms of their existence would have changed, because the giant reservoir that partnered with the land in every season was gone. Perhaps the most unsettling feature of these first days would be the mismatch between visibility and understanding. Humanity would be able to see more of Earth's physical surface than ever before, yet the meaning of what it saw would exceed immediate intuition. A dry, abyssal plain might look empty, though it records sedimentation, plate motion, and biological rain over millions of years. A ridge might look like a distant mountain chain, though it marks crust being born. A trench might appear as a dark boundary, though it is a site where one plate descends beneath another. The revealed ocean floor would therefore demand interpretation, even as it inspired awe. Geologists, oceanographers, biologists, climatologists, and chemists would all be looking at the same new world, each reading a different layer of its meaning. That, too, belongs to the strangeness of the event. The Earth would be more exposed and more difficult to comprehend at the same time. The first week, then, would not yet be dominated by the full climatic unraveling to come. It would be dominated by revelation. The Earth would appear to have split open without actually breaking. Every coast would become an overlook. Every continent would inherit new frontiers. Every old maritime chart would become a geological sketch. Scientists would suddenly find the hidden topography of the planet lying in the open, while at the same time losing the very system that made much of the planet habitable. It would be a paradox of knowledge and catastrophe. Never before would so much of Earth be visible, and never before would the consequences of visibility be so severe.
This is why the early stage of a dry Earth must be understood not as a single event, but as an unfolding argument between surface and system. First, the water is gone. Then geography changes. Then habitats collapse. Then the atmosphere begins to realize what has been lost. The order matters. The exposed seafloor, as dramatic as it is still only the beginning of the story. Beneath the awe of this revealed landscape lies a deeper truth. The ocean was not merely covering the planet. It was governing exchanges, moderating extremes, feeding clouds, sustaining currents, and linking distant regions through a cycle so continuous that it usually disappears into the background of life. And so, after the first stunned gaze across shelves, slopes, ridges, and trenches, attention would inevitably rise from the ground to the sky. Because once the great blue surface is gone, the next question is no longer what Earth looks like, but how long the old Earth can still behave like itself. The clouds overhead would still drift. Rain might still fall in some places. Rivers would still move for a time, but all of them would now belong to a dwindling inheritance,
And the long unmaking of the familiar world would begin not on the seafloor, but in the air above it. The sky would keep moving for a while, and that would make the change more unsettling, not less. Clouds would still drift across continents. Dawn would still stain their edges with gold. Afternoon shadows would still pass over mountains, cities, forests, and the newly exposed continental shelves. A storm might even break somewhere over land in those first days, with rain striking roofs and roads as though nothing fundamental had happened. But the old certainty behind weather would already be gone. The air above Earth would now be living on stored water, drawing from a reserve that was no longer being renewed by the great evaporating surface that once covered most of the planet. That surface had been doing far more than reflecting the sky. The oceans were the dominant source of water vapor entering the atmosphere. Sunlight warmed their upper layers, winds disturbed them, and every second across an area larger than all the continents combined, molecules of water escaped upward into the air. This continuous transfer was one of the quiet foundations of the water cycle. It fed humidity, cloud formation, rainfall, snowfall, and the endless transport of moisture from one region to another. Without oceans, that planetary exchange would not slow, it would stop. The distinction matters. A world in which evaporation becomes weaker is still familiar. A world in which the main evaporating engine disappears entirely becomes something else. At first, the atmosphere would still contain vapor already present before the event. Lakes, soils, vegetation, rivers, wetlands, and remnant ice would still release some moisture into the air. Evaporation would not become zero, but the scale would be transformed so dramatically that the word evaporation itself would start to mean something smaller than it once did. The modern sky is a sky fed by oceans. The sky above a dry Earth would be trying to continue on continental leftovers because the atmosphere is dynamic, not static. Moisture would not vanish from it all at once. Winds would continue moving air masses around the globe. Clouds would continue condensing where temperature and pressure allowed. Rain and snow could still fall in the short term. But what was once part of a self-renewing cycle would now become a drawing down of inventory. Each cloud would be spending a little of a reserve that had taken shape while the oceans still existed. Each rainfall would be one more redistribution of water inside a system whose deepest reservoir had been erased from the surface. On a living Earth as we know it, more water evaporates from the ocean than falls back directly into it,
while over land, more precipitation falls than evaporates. Rivers then carry that excess fresh water back toward the sea, closing the loop. It is one of those elegant imbalances that makes the whole arrangement work. The ocean gives vapor to the sky gives rain to the land returns water through rivers. With the oceans removed, the loop breaks at its largest point. Vapor still leaves lakes and soil, water still moves downhill, but the broad planetary exchange between ocean, atmosphere, and continent no longer exists in its old form. This would change the character of weather long before it changed the deeper climate averages that scientists usually discuss. Weather is the daily face of the atmosphere, and that face is shaped by moisture as much as by temperature. A dry atmosphere behaves differently from a moist one. Water vapor affects cloud formation, precipitation, heat transport, and the amount of energy released when water condenses. Some of the most powerful storms on modern Earth, from tropical cyclones to monsoon systems, depend on warm ocean water and the vast transfer of moisture into the air above it. Deprived of that source,
the planet would gradually lose some of the very processes that currently make its weather dramatic. To understand why, it helps to linger for a moment on the ordinary miracle of evaporation itself. Water molecules in liquid form are held together by attraction, and only a fraction at the surface have enough energy to escape into the air. Sunlight and warmth make that escape more likely. Wind removes humid air from the surface and replaces it with drier air, allowing more molecules to leave. Over the ocean, this exchange has been occurring on an unimaginable scale for millions of years. The sea does not need to boil to fill the sky. It breathes upward in countless invisible escapes. Remove that breathing, and the atmosphere begins to age. There would still be moisture trapped in soils, especially in humid regions. Forests would continue releasing water vapor through transpiration, the process by which plants draw water up from roots and release it through leaf pores. This is sometimes described as plants sweating, though the mechanism is different. It is one reason rainforests help sustain their own humidity. Some continental regions today recycle a significant fraction of their own rainfall through vegetation and local evaporation. But this recycling has limits. It depends on an initial supply. If the large-scale input from the oceans disappears, then even the greenest regions eventually begin to dry from the edges inward. Their own recycled moisture becomes weaker with each turn. The first regions to feel this most clearly would likely be those already balanced near the threshold between wet and dry. Semi-arid lands, monsoon margins, seasonal grasslands, Mediterranean climates, and places where rainfall arrives in narrow windows of time would begin to shift quickly. But even famously rainy regions would be living on borrowed time. The temperate coasts of Western Europe, the eastern seaboards of continents, the maritime fringes of mountain belts, the humid tropics, the great river basins fed by monsoon systems all ultimately depend on ocean-fed air. Their rains are local in experience, but oceanic in origin. If you could watch Earth from orbit over the first several weeks and months, one of the most remarkable changes would be in cloud patterns. The long ribbons and rotating systems that usually organize over warm oceans would weaken or disappear. The great cloud streets above current-rich waters, the spiraling birthplaces of tropical storms, the broad, humid fields associated with trade winds and marine evaporation would fade. There might still be clouds where mountains force air upward, where remaining lakes add local moisture, or where temperature contrasts create instability, but the planetary cloud architecture would become patchier, less oceanic,
less sustained. The atmosphere would look like it had lost part of its memory. The tropical belt would be altered profoundly. Today, the tropics are defined by abundant solar energy and, over the oceans, vast evaporation. Warm air rises, moisture condenses, and immense towers of cloud build and collapse in cycles that help drive global circulation. The intertropical convergence zone, monsoon systems, and tropical convection are all intertwined with the presence of warm surface water. Remove the oceans, and the tropics do not become cold. They become dry in a way that changes the style of their heat. Instead of warm, humid air rising from sea surfaces day after day, broad regions of exposed seafloor and desiccating land would radiate and convect heat differently, with far less moisture available to turn that heat into rain. Humidity itself would become something more precious and more local. A humid day in the modern world often arrives because air has traveled over water, or because recent rainfall has left the landscape wet enough to feed the air above it. On a dry Earth, many humid days would be remnants of conditions that could no longer sustain themselves for long.
Morning fog might still form over certain valleys. Mist might still rise near lakes or wetlands, but the heavy, persistent, ocean-borne humidity that now defines tropical coasts and many temperate maritime climates would withdraw. Air would begin to feel thinner in the sensory rather than literal sense, stripped of the softness that moisture gives it. The reduction in rainfall would not unfold evenly across the globe. Geography would matter. Mountains would still force air upward, wringing water from what moisture remained. Regions near large surviving lakes, extensive wetlands, or major remaining ice masses could still generate localized precipitation for longer than regions with little stored water. The interior of continents might not always dry faster than coasts in a simple way, because the old meaning of coast would no longer apply. Some former coastlines would now overlook vast exposed shelves and basins that contributed little or no moisture to the air. A city, once considered maritime, could suddenly behave like the edge of a desert plateau. Seasonality would also begin to shift in subtle ways before becoming more obvious. Many regions on modern Earth have rainy seasons tied to ocean temperature contrasts, seasonal wind reversals, and the slow warming and cooling of seawater. Without oceans, those patterns would weaken or vanish. Some lands would still have seasonal changes driven by the tilt of Earth's axis, the length of day, and snow cover, but the familiar timing of moisture would come apart. Places that once relied on a dependable wet season would see it shrink, drift, fail, or arrive in a diminished form. Agriculture, ecosystems, and river systems are all tuned to timing, not just total amounts. A world that still receives some rain, but no longer receives it on the old schedule, is already becoming difficult to inhabit. The monsoon is perhaps the clearest example of this dependence. Monsoons are not simply heavy rains. They are seasonal wind and precipitation systems created by differential heating between land and ocean, along with the movement of pressure belts and the supply of marine moisture. South Asia, parts of Africa, northern Australia, and other monsoon regions support immense populations and ecosystems structured around this annual pulse. Without adjacent or nearby oceanic moisture sources, a monsoon cannot operate in the familiar way. The heating contrast might still exist in some weakened, transformed form between different dry surfaces or between land and remnant inland waters, but the central ingredient of abundant ocean-fed vapor would be missing. The great annual arrival of rain
would become uncertain, then faint, then absent. As rainfall diminished, the planet's rivers would begin to tell the story in plain language. At first, many would continue flowing because rivers integrate water over time. Snowmelt, already stored in mountain packs, would still descend in spring. Groundwater would still seep into channels. Lakes already full would still drain. Large river systems do not stop the same day that rain becomes less common. But the important thing about rivers is not that they carry water. It is that they reveal the balance between supply and loss across a landscape. On a dry earth, every major river would begin, sooner or later, to announce that the supply side was failing. Take a mountain-fed river. Snow and glacier melt may sustain it for months or years, depending on the size of the ice reserve and the new temperature regime. In the short term, some rivers might even surge if destabilized ice or altered runoff patterns release stored water more quickly. But glaciers are savings accounts, not income. Without regular replenishment from snowfall, they shrink. Once they have given what they stored, the flow they once supported weakens. Rivers descending from high mountain systems such as the Himalaya, Andes, Alps, Rockies,
or Southern Alps would therefore enter a new hydrological future in which their initial endurance masked their eventual fragility. Rain-fed rivers would respond more directly. Streams that depend on seasonal storms could become intermittent very quickly. Tributaries would dry first, then smaller channels, then broader reaches. Floodplains would lose their regular inundation. Wet meadows would contract. Groundwater recharge would fall. The banks of rivers that once spread and braided across deltas would harden, crack, or become invaded by salt and dust, depending on their location. In some basins, flow might persist for a long time, where aquifers continue feeding channels. In others, whole drainage networks could fragment into disconnected pools and dry reaches. The great river mouths would be especially transformed. Today, they are where continents finish a sentence the sea completes. In a dry world, that completion never comes. Rivers reaching the edge of the former continental shelf would not enter estuaries and coastal waters. They would descend into exposed marine topography, perhaps carving new channels into the soft sediments of the shelf plain, perhaps pooling in low areas, perhaps sinking into porous deposits, perhaps eventually continuing toward deeper basins if their volume allowed. Some might create temporary inland seas in topographic depressions. Others would simply fade, their discharge no match for evaporation and infiltration across the newly opened expanse. Lakes would become the most visible remaining pieces of surface water, and their fates would vary dramatically. Deep, cold lakes with large catchments and modest evaporation might endure for a time as regional hydrological refuges. Shallow lakes in dry climates could shrink quickly, leaving salt flats or muddy basins. Endorheic lakes, those with no outlet to the sea, already live in a delicate balance between inflow and evaporation. Without ocean-fed weather patterns sustaining their watersheds, many would retreat or vanish. The Aral Sea offers a modern, human-caused example of how dramatic lake shrinkage can reshape local climate, dust production, and ecosystems. A dry Earth would repeat that lesson on a planetary scale. This is where the relationship between water and climate becomes especially circular. Less evaporation means less precipitation. Less precipitation means less river recharge, less soil moisture, and smaller lakes. Smaller lakes and drier soils,
then contribute less evaporation back to the atmosphere, which further reduces local and regional humidity. Vegetation weakens, which reduces transpiration, which further dries the air. The result is not just a one-time loss, but a feedback. Earth would not simply miss the oceans. It would begin adjusting to their absence by becoming less capable of holding on to the hydrological patterns that once depended on them. Soil moisture is easy to overlook in discussions of planetary systems, yet it is one of the hidden links between rain and life. Moist soils buffer temperature, support plant roots, feed streams, moderate dust, and keep microbial processes functioning. As rains declined, soils would dry at different rates depending on texture, organic content, vegetation cover, depth, and climate. Sandy soils lose water quickly. Clay-rich soils can retain it longer, but may crack dramatically when they dry. Organic-rich soils shrink and oxidize. Where soils lose moisture, the land surface itself changes its behavior, warming more rapidly by day, cooling differently by night, and releasing more particles to the air. Dryness becomes not just a lack of water, but a new physical state of the land. Vegetation would therefore begin signaling the change even before many trees died. Leaves would close pores to conserve water, reducing transpiration. Growth would slow. Seasonal stress would deepen. Grasses might fail to green in years or seasons when they once did. Wetlands would contract,
exposing dark organic sediments that could oxidize, crack, or burn. Peatlands, where they remained, would become vulnerable in new ways because they depend on persistent saturation. Forest edges would dry. The soundscape of living landscapes would begin to shift with the water budget. Less running water, fewer amphibians, fewer insects tied to standing water, fewer birds drawn to wet margins. The hydrological retreat would have a sensory character long before every map caught up. By this point, the planet's temperature patterns would also be starting to change in a more obvious way. Oceans do not merely provide moisture, they act as thermal reservoirs of astonishing scale. Because water has high heat capacity, it can absorb huge amounts of energy with relatively modest temperature change, and it releases that energy slowly. This is one reason coastal cities often have cooler summers and milder winters than inland cities at similar latitudes. It is one reason the global climate system can transport and store energy in ways that smooth regional extremes. Remove the oceans, and the world loses a major stabilizer. What replaces them on the surface are former seabeds made of rock, salt, sediment, and dust-prone material, all of which generally respond to heating and cooling more quickly than deep water. During the day, many exposed marine plains would heat rapidly under direct sunlight. At night, under clear, dry skies, they would radiate heat back into space efficiently and cool quickly. The result would be larger daily temperature swings, especially in dry regions. A place that was once moderated by nearby sea could become blistering by afternoon and sharply cold before dawn. This is already familiar in deserts, where limited moisture and clear skies allow strong day-night contrasts. The difference is that, on a dry Earth, desert-like behavior would spread into regions that had never known it. Seasonal contrasts would also intensify in many areas, though not everywhere in the same way or on the same timeline. Without nearby ocean heat storage, continental interiors would become even more continental, responding more directly to seasonal changes in solar input. Winters in high latitudes and interiors could become more severe in some respects because little nearby water would remain to release stored warmth into the atmosphere.
Summers in subtropical and temperate interiors could become hotter because exposed land and seabeds would absorb and re-radiate heat without the moderating influence of large water bodies. The phrase climate change often evokes gradual shifts in averages, but what people would feel most immediately is a new violence in temperature range. The coast has always been one of Earth's great mediators. Think of Western Europe, where the Atlantic and its heat transport help keep winters milder than latitude alone would suggest. Think of California's marine influence, the cool summer air along parts of Peru and Chile, the monsoon interactions of the Indian Ocean, the humidity of the Gulf, the cloud belts of the Southern Ocean, the moderation of Japanese and Korean coasts, the gentle marine climates of New Zealand. Without ocean water, none of these places remain the climates they once were. Their latitudes stay the same, their mountains remain where they are, but the thermal conversation that defined them ends. Weather maps would still show fronts and pressure systems, yet the baseline beneath them would have shifted. Ocean currents, though no longer currents in the ordinary sense because the water itself is gone, deserve a moment of attention here because they are one of the chief ways oceans shape climate. The Gulf Stream system, the Antarctic circumpolar current, upwelling zones along certain coasts, equatorial current systems, and deep overturning circulation all redistribute heat and nutrients. They are not decorative movements. They are architecture in motion.
Without oceans, there would be no marine heat conveyor, no transport of warm tropical water poleward, no cold upwelling to fertilize coasts, no deep circulation storing carbon and oxygen in characteristic ways. Even before the atmosphere reached a new equilibrium, the disappearance of these flows would remove a dynamic order that had quietly conditioned temperatures across whole hemispheres. Sea ice would disappear not by melting first, but by losing its sea. In the Arctic, floating ice forms on ocean water, moves with winds and currents, and insulates the sea while also reflecting sunlight. Without the ocean, the very category of sea ice becomes unstable. Some ice would likely collapse into exposed basins, fragment, sublimate, melt seasonally, or remain temporarily grounded depending on local conditions. But the reflective lid over the polar ocean would no longer function as it once did. This matters for climate because sea ice influences albedo, exchanges between ocean and atmosphere, and the seasonal behavior of polar regions. Antarctica's grounded ice sheet would persist much longer than floating ice because it is stored on land, but its margins and surrounding ice shelves would be radically altered by the loss of supporting seawater. Albedo, the measure of how much sunlight a surface reflects, would become a complex piece of the new climate story. Some exposed former sea floors, especially salt-rich flats or light-colored sediments, might reflect significant sunlight. Others, especially darker volcanic or organic-rich surfaces, could absorb more. The ocean itself is not uniformly bright or dark in climatic terms because reflection changes with sun angle, cloud cover, ice cover, and wave state. A dry Earth would therefore not simply become uniformly hotter or uniformly cooler in every place based only on color. What changes more clearly is the combination of reflectivity, moisture availability, and heat storage. A pale salt pan may reflect sunlight, yet still create a harsh, dry atmosphere because it holds little water and releases energy differently from an ocean surface. This is where caution matters. In an extreme thought experiment, it is tempting to summarize too quickly, as though one sentence could describe the new global average climate.
But climate is an arrangement of interacting processes. Some places might temporarily cool relative to their ocean-influenced past because evaporative and cloud-related greenhouse effects weaken, or because new reflective surfaces emerge. Other places might become dramatically hotter in daytime because moisture no longer buffers heat. Some seasonal patterns might produce bitter cold under dry, clear skies. Others could produce devastating heat over exposed basins. The broad and safe conclusion is not that dry Earth becomes simply hot or simply cold. It becomes less buffered, less oceanic, more extreme, and more regionally unequal. As humidity declines and temperature swings widen, the air itself would begin to behave differently around the surface. Moist air stores and releases latent heat through condensation and evaporation. Dry air does less of this. Moisture also affects how the human body experiences temperature, how clouds form, how long heat lingers at night, and how energy is partitioned between sensible heating of the air and latent heating tied to water. On a drying Earth, more incoming energy in many areas would go into directly heating the land surface and adjacent air because less water would be available to evaporate. The tactile result would be a world that feels harder. Sunlight would feel less softened by haze and humidity. Shade would still matter, but the transitions between warm and cool, wet and dry would grow sharper. Wind would carry a new importance. In some regions, broader exposed shelves and basins would create long fetches across dry surfaces where air could accelerate unhindered. Once those surfaces dried sufficiently,
Winds could lift fine sediments, salts, and dust into the atmosphere. The former seafloor in many places would contain vast quantities of unconsolidated material. Without water to hold it down and without vegetation to bind it quickly, some of these surfaces could become major dust sources. Modern Earth already has examples of dried lake beds and exposed saline basins generating intense dust storms, sometimes with severe health effects due to salt, heavy metals, or fine particulates. Multiply that process across continental shelves and inland remnant basins, and the atmosphere gains a new burden. Salt would be a defining material of this altered world. The oceans today contain dissolved salts that are kept in motion, diluted, and largely invisible at human scale, except where evaporation leaves them behind. When marine basins dry, salts are concentrated and deposited. Exposed shelf areas, enclosed former seas, tidal flats, lagoons, and low marine depressions could therefore become enormous repositories of evaporite minerals and salt-rich sediments. Even in places where the ocean vanished instantaneously, rather than through prolonged evaporation, the residues left in saturated sediments, brines, and near-surface materials would matter. Winds crossing these zones could carry salt particles inland. Soils near them could become contaminated. Surviving freshwater systems could face salinization from intrusion into exposed marine sediments and altered groundwater flow. Dust and salt together would reshape the atmosphere in ways both local and potentially broader. On the local scale, air quality near newly exposed marine basins could become extremely poor. Fine particles irritate lungs, reduce visibility, and affect human health, agriculture, and ecosystems. Salt-laden dust can damage vegetation and infrastructure.
On the regional or larger scale, airborne particles influence sunlight, cloud microphysics, and the radiative balance of the atmosphere. Again,
it would be reckless to claim a single, simple, global outcome from these aerosol changes, but it is entirely plausible that the disappearance of oceans would create new major dust provinces whose influence extended far beyond the former shore. The former shallow seas of places like the North Sea, the South China Shelf, the Bering Shelf, the Sunda Shelf, or the broad margins of Patagonia and the Arctic would be especially significant in this regard. These are not tiny coastal strips. Some continental shelves are enormous. Exposing them would add millions of square kilometers of new land-like surface, much of it sediment-rich, biologically active, and physically fragile at first. What had been among the world's most productive marine zones could become among the most chemically and physically difficult surfaces to inhabit. The change from nursery water to dust-producing plain would be one of the sharpest examples of how radically different a surface becomes when its medium changes. The interiors of the great former ocean basins would likely present a different but related challenge. Deep sea sediments often accumulate slowly and can include very fine clays and biological oozes. Under open air, once dried, some could behave like powder or crust, depending on composition. Large areas might initially remain too moist or unstable to loft dust easily, while others, especially where wind exposure is great and surface crusts break down, could begin contributing fine particles over time. The timing would matter. The first weeks might be dominated by exposure and collapse. The months and years after could increasingly be defined by aeolian processes, the movement of material by wind. Ancient seabeds would begin to behave like deserts, but deserts with unusual chemistry and structure. The smell of the planet would change too. This may sound minor beside climate, but smell is often the most intimate sense by which environments become real. Tidal flats, drying algae, salt marshes, fish-rich coasts, and marine air each have distinctive scents tied to biology and chemistry. A vanished ocean would not leave behind a neutral vacuum. Drying organic matter on shelves, exposed anoxic sediments, sulfur-bearing minerals, salt-crusted flats, and newly oxygenated seabeds could create odors never before associated with certain regions. Some would fade as materials oxidized and decomposed. Others would persist seasonally or locally. The familiar scent of sea air, so bound up with human memory and geography, would disappear almost instantly, replaced first by shock, and later by the mineral breath of a dry basin. By now, the old hydrological elegance of the world would be noticeably fraying. Rain would be less frequent and less reliable. Rivers would still run in some regions, but under declining support. Lakes would become strategic and ecological anchors. Glaciers would continue supplying water where they remained, yet without assured replenishment. Vegetation would begin to surrender moisture-saving signals. Dust and salt would rise from newly exposed flats. The atmosphere would no longer look like the self-renewing sky of an ocean planet. It would look like a sky trying to continue after losing its largest partner. The idea of buffer is useful here because it describes what oceans do without requiring drama. They buffer temperature. They buffer humidity. They buffer seasonal change. They buffer, in many cases, ecological stress. Remove them, and events that once would have been softened become harsher. A hot week becomes more punishing. A failed rainy season becomes more consequential. A dry wind becomes more dangerous to soil and crops.
A frozen night becomes more severe under clear, desiccated skies. The world does not need to become apocalyptic in one gesture. It only needs to become less forgiving, less replenishing, less capable of absorbing disturbance without amplifying it. There is also a longer chemical story beginning here,
though its full importance would emerge later. Ocean water today absorbs carbon dioxide, exchanges gases with the atmosphere, and participates in one of the great balancing acts of planetary chemistry. The loss of that vast liquid interface would alter how gases move between Earth's surface and the air. This would not be the first thing people noticed, nor the first thing ecosystems responded to, but it would already be part of the unfolding transformation. A dry Earth would not simply lose rainfall and moderation. It would begin losing one of the central exchange surfaces through which the planet manages its atmospheric composition over short and long timescales. For human communities, the most immediate climatic change would not necessarily be one global disaster visible everywhere at once. It would be the breakdown of trust in patterns. Farmers would realize rains were failing outside their historical bounds. Reservoir managers would find inflow no longer matching expectation. Mountain communities would see snowpack behaving like a finite inheritance instead of a seasonal return. Coastal cities, now inland in effect, would discover that the marine influence they had long taken for granted had vanished with startling speed. Shipping would already be impossible. Ports would already be useless. But the deeper unease would come from the sky, from the realization that weather itself no longer belonged to the stable world in which human civilization had learned its timing. This is why the disappearance of oceans would be more than a geographic impossibility. It would be the breaking of a machine whose moving parts are often invisible precisely because they are so continuous. Evaporation, condensation, runoff, heat storage, humidity transport, seasonal moderation, cloud formation, monsoon timing, river recharge, albedo feedbacks, dust suppression, salinity balances, and the chemistry of living surfaces all interlock. In ordinary times, one can study each piece separately. In this imagined world, the removal of the ocean would show how dependent every piece was on the whole. It would make the hidden scaffolding of climate visible by destroying it. And still, despite all this unraveling, some water would remain. That fact would begin to define the next stage of the story. Fresh water stored in rivers, lakes, wetlands, aquifers, mountain ice, and soils would become disproportionately important because it would be all that was left at the surface to sustain climates, ecosystems, and eventually human choices. The great salt reservoir of the sea would be gone. What remained would be the scattered, uneven, vulnerable freshwater body of the continents. It would no longer be a small part of a global cycle supported by the oceans. It would become the center of attention, the fragile inheritance of a world learning what life without seas really means. And once the atmosphere had begun to thin of moisture, and the land had started to harden under a harsher sky, the question would shift again, from the failure of the climate machine to the places where water still moved at all, and to the long, uneasy fate of the rivers that had once known exactly where they belonged. Groundwater would become more important precisely because it is less visible. Beneath many landscapes, aquifers store water accumulated over years, centuries, sometimes much longer. Springs, baseflow, wetlands, and many dry season river channels depend on these hidden reserves.
In a world without oceans, aquifers would briefly seem like stability itself because they would continue feeding streams after rains failed. Yet groundwater is only slow water, not endless water. Some aquifers recharge rapidly from regular precipitation. Others are ancient and replenished so slowly that, on human timescales, they are closer to deposits than incomes. As recharge weakened almost everywhere,
Many rivers would continue moving only because they were spending what had been stored beneath the land long before the seas disappeared. Snow would tell the same story in another form. Snowpack is seasonal memory. It preserves cold season precipitation and releases it gradually when temperatures rise. In mountain regions, this release smooths the year, sustaining downstream soils, cities, farms, and ecosystems through dry months. But snow without continued snowfall becomes a countdown. At first, high peaks might still gleam, and spring melt might still surge into channels with enough force to suggest continuity. Yet each season would empty the reservoir further. The white brilliance that once promised renewal would become a measure of what remained to be lost. Even the language of ordinary weather would begin to feel outdated. Forecasts might still speak of fronts, pressure, showers, frost, wind, and heat, but the deeper context behind those words would no longer be the one in which they evolved. A storm would not mean what it once meant if no warm sea remained to build the next one. A drought would no longer be a temporary failure inside a larger, stable system. It would be the new direction of the world, and every drying stream, every shrinking lake margin, every dust haze rising from an exposed marine plain would say the same quiet thing in different ways. The Earth was not merely losing water from its surface. It was losing the conditions that had always returned water after its absence. Soon, that change would no longer be read only in clouds and rivers, but in harvests, coastlines, cities, and habits of survival. From that point on, water would no longer be a background condition of life. It would become the visible center of every map, every migration, every harvest, every settlement, and every fear. The world had once been organized around abundance so large that most people never thought of it as abundance at all. Oceans had made the planet feel generous by being everywhere at once, by storing and moving what no civilization could ever store or move for itself. Without them, the remaining fresh water of the continents would stop feeling ordinary. It would begin to look like scattered light after a power failure, still shining in places, but no longer joined into one vast and reliable system. The first great human crisis would not come from the exposed abyssal plains, however astonishing they were. It would come from food. The ocean has always fed humanity directly through fish, shellfish, marine mammals in certain traditions, algae, and the enormous economic web built around them. But it also feeds human societies indirectly through climate moderation, rainfall patterns, nutrient transport, and the stability of coastlines and seasons. Remove the sea, and the fishing fleets do not merely lose access to their grounds, they lose the existence of their grounds. Harbors become cliffs above empty basins. Coastal processing plants fall silent. Refrigerated supply chains become irrelevant. Entire cuisines, economies, and inherited skills survive only as memory.
Even that would still be only the beginning, because the marine food web does not end at the shoreline. Seabirds connect land to sea. Migratory fish once carried oceanic nutrients into rivers. Coastal wetlands sheltered juvenile life stages of countless species. Coral reefs and shallow banks supported local fisheries that, in turn, supported human populations. Some modern agricultural systems are linked to marine-derived fertilizers, shipping routes, and climate patterns shaped by ocean heat. On a dry Earth, the collapse of marine life would therefore widen outward, like ripples from a vanished center. The first shock might be counted in lost catches and empty ports. The deeper shock would appear in the gradual realization that the sea had been nourishing land in ways most people never saw.
Agriculture would enter a new age almost immediately, though not an age of invention so much as an age of reduction. Crops depend on timing, temperature, soil moisture, groundwater recharge, and predictable seasons. As rainfall declined and the thermal buffering of the oceans disappeared, those conditions would begin to separate from the patterns in which agriculture evolved. Fields, once watered by dependable rains, would require irrigation. Irrigation would then compete with cities, ecosystems, and industry for shrinking freshwater reserves. In regions where rivers were fed by snowpack or glaciers, there might be a brief illusion of security, but only while those frozen reserves lasted. The long trend would still point toward scarcity, because a shrinking reservoir cannot support permanent expectations. The vulnerability would not be the same everywhere. Some places would still have deep lakes, substantial groundwater, cool mountain runoff, or climatic refuges where clouds lingered longer than elsewhere. Others, especially those already near aridity, would fail quickly. Irrigated agriculture in dry regions depends on stable rivers or stored groundwater. Rain-fed agriculture depends on seasonal reliability. Both would be threatened, but in different ways. A breadbasket can fail from too little water, but also from badly timed water, from heat waves arriving at the wrong stage of growth, from soils drying too quickly between storms, from wind erosion, from salinity, or from the simple loss of confidence that next season will resemble the last one. Under those conditions, famine would not always arrive as a single dramatic event. Often it would arrive as a pattern of smaller failures that no longer corrected themselves. The drying of the world would also divide species into very unequal futures. Large marine animals would already be gone, or nearly gone. Many coastal systems would have collapsed. But on land, survival would depend less on size or strength than on flexibility, water access, and the ability to endure new thermal extremes. Specialists would suffer first. Species tied to wetlands, estuaries, amphibious breeding sites, cool coastal forests, or humid seasonal patterns would face intense pressure. Generalists, especially those able to move widely, exploit varied foods, or survive in disturbed habitats, would hold on longer. This is a pattern already visible in human-driven ecological change. Under the disappearance of the oceans, it would intensify beyond anything seen in recorded history. Forests would become mosaics of persistence and retreat. Not every forest would die at once. Mountain forests near surviving snow and groundwater could endure for long periods. Tropical forests with deep moisture reserves and complex internal humidity might resist for a time, especially where topography helped trap rainfall or cloud. But their resistance would not mean immunity. Large forests create some of their own climate through transpiration and shade, yet they cannot fully replace the planetary moisture that oceans once supplied. Over years and decades, edges would dry.
Fires would become more likely in some regions, and species adapted to continuously humid conditions would retreat toward dwindling refuges. The green map of Earth would not vanish in one motion. It would fray. Grasslands and savannas would tell a similar but more subtle story. Some are already adapted to seasonal water stress, fire, and temperature swings. In a drier, more extreme world, such systems might persist where deeper-rooted vegetation and periodic rain still allow them to function. Yet they too depend on thresholds. Push the rainfall too low, push heat too high, reduce recharge too far, and a grassland can become sparse scrub, then open dust-prone ground. Where herbivores once moved across rich plains, there could remain only fragments of forage around rivers, springs,
and managed water points. The continuity of habitat would break, and with it, the great migrations that depend on space as much as on food. Human civilization, meanwhile, would discover how deeply it had built itself around the geometry of water. Many of the largest cities on Earth are coastal, not by accident, but because coasts concentrate movement, trade, moderate climate, and access. New York, London, Tokyo, Shanghai, Mumbai, Buenos Aires, Lagos, Los Angeles, Alexandria, Jakarta, and countless others grew where rivers met the sea, or where harbors opened onto shipping routes. Without oceans, these places would not simply lose economic advantages, they would lose the original physical logic of their existence. A port city with no port is not merely a poorer city, it is a city whose relationship to the world has been severed. Transport networks would be forced inland, but that phrase hides almost unimaginable difficulty. Roads and rail can move goods, but not with the same ease, scale, or energy efficiency as ships crossing open water. Bulk trade would contract. Global supply chains, already fragile even in ordinary disruptions, would become impossible to sustain in their old form. There would be no maritime highways linking continents, no tankers, no container routes, no ferries, no deep water export terminals. The oceans were not empty gaps between productive lands. They were the cheapest movement surface on the planet. Civilization used them not because it was romantic, but because physics favored buoyancy. Remove buoyancy, and trade becomes heavier, slower, more localized, and more expensive in every sense of the word. The industrial landscape would change accordingly. Desalination plants, where they existed, would no longer matter because the sea itself would be gone. Coastal refineries, shipyards, fisheries infrastructure, naval bases, offshore energy platforms, and entire waterfront industrial belts would become artifacts of a finished era. Some inland industries might adapt around remaining freshwater reserves or new land routes. Others would simply stop. Energy systems would also be strained. Hydropower would eventually weaken where river flow declined. Thermal power plants require cooling water. Nuclear plants, too, depend on reliable cooling. Water treatment, pumping, and transport would consume more energy, just as the systems supporting stable energy distribution grew harder to maintain. Shortage would therefore be ecological, economic, and mechanical at once. Freshwater would become the defining political fact of the world. In the modern age, nations already contest rivers, aquifers, and watersheds. On a dry Earth, those disputes would no longer sit at the margins of geopolitics. They would become geopolitics. A Great Lake would be as strategic as an oil field once was. A stable mountain watershed would be guarded like a treasury.
aquifers crossing borders would become zones of intense negotiation or conflict. Regions that once exported food might stop feeding themselves. Regions that once seemed climatically marginal could become refuges if they retained snow, springs, or cloud-fed uplands. Migration would follow water, not ideology. Yet, even under extreme stress, it would be wrong to imagine that all humans vanish quickly. Human beings are highly adaptive, technically skilled, and capable of building artificial environments. We already live in deserts, polar regions, mountains, deltas, and dense cities. By moving water, storing food, insulating buildings, drilling aquifers, treating wastewater, and constructing infrastructure that no other large species could maintain. In the early and middle years of a dry Earth, many societies would survive precisely because they could concentrate knowledge and engineering around remaining water. Reservoirs would be extended, pipelines would be built, recycling would become universal where possible. Agriculture might retreat into protected,
Efficient systems in some places. Survival would be unequal, but it would not be absent. The deeper question would be scale. Human ingenuity can stabilize a city, a valley, a network of settlements, perhaps even a continent-spanning system for a while. It cannot replace an ocean. Civilizations function because they borrow from planetary processes larger than themselves. Rainfall, soil formation, river flow, pollination, seasonal predictability, and the thermal moderation of the climate system. Technology can delay collapse, soften local hardship, or concentrate scarce resources. It cannot easily rebuild the background stability that billions of years of Earth history created through atmosphere, water, rock, and life. The disappearance of the oceans would therefore expose the true proportions between human power and planetary power. We would remain clever, but our cleverness would be operating inside a narrower and harsher world. Where, then, would life endure the longest? The answer would lie in refuges, and refuges are never distributed evenly. High mountains would matter because they store cold, snow, and runoff. Deep freshwater lakes would matter because they preserve local climate and biodiversity longer than shallow waters. Certain shaded valleys, cloud forests, groundwater-fed wetlands, and polar or subpolar regions could become pockets of persistence, while surrounding lands grew harsher. Underground systems would matter too. Caves, deep aquifers, and subsurface microbial habitats already hold life insulated from surface extremes. If the question is not where life thrives, but where life lingers longest, then the most durable answer may not be the broad green surface we associate with abundance, but the hidden or topographically protected places where moisture remains difficult to steal. Microbial life would likely prove the most resilient, as it so often does in Earth history. Microbes live in rock pores, sediments, aquifers, hydrothermal systems, polar ice, desert crusts, and subsurface environments far removed from sunlight. Many can endure extreme salinity, cold, heat, desiccation, or chemical stress. Some would die with the collapse of marine habitats. Others would persist in damp sediments, underground waters, or chemically favorable niches. This matters philosophically as much as biologically. A dry Earth would still be alive long after it ceased to be comfortable for the large, visible life forms that dominate human imagination. The planet would become harder for animals and plants as we know them, yet the smallest forms of life would continue finding footholds in the margins. Among larger organisms,
Freshwater species in protected basins might survive much longer than marine life had. Fish in deep lakes, amphibians in durable wet refuges, birds following the last rivers, mammals clustering around water sources, and hardy plants adapted to cold or drought would all have chances measured not in certainty, but in delay. Delay matters in extinction stories. The end of a stable world is rarely a single synchronized moment for every species. It is a moving boundary. Some forms vanish immediately, some fade slowly, some adapt, some relocate, some persist in enclaves long after the larger system that once supported them has collapsed. Earth's fossil record is full of these uneven endings. This unevenness would reshape human feeling toward geography. Places that once seemed peripheral could become central. A cold plateau with reliable glacial melt might matter more than a former breadbasket. A cloudy mountain arc might matter more than a vast plain. Regions close to the old coasts might, in some cases, become less valuable than interior watersheds if the newly exposed basins created heat, dust, salt, and instability instead of opportunity. The meaning of habitability would shift from access to trade and fertile lowlands toward access to long-term water and temperature moderation. Civilization,
if it persisted in organized form, would redraw not just borders, but its idea of what makes a landscape worth inhabiting. All the while, the planet itself would remain geologically alive. This is essential to remember. The oceans disappearing from the surface would not turn Earth into a dead stone. Heat would still rise from the interior. Volcanoes would still erupt in some regions. Continents would still drift, though the role of water in certain tectonic processes means the long-term details of that drifting would become more complex and perhaps altered in ways difficult to predict confidently. Subduction zones, mountain building, faulting, mantle convection, and crustal recycling are not surface decorations. They are expressions of a deep planet continuing its slow work. Even under the most severe surface transformation, Earth would still be Earth. The exposed mid-ocean ridges and trenches would make this especially vivid. What had once been hidden evidence of plate tectonics would stand in the open. Rift valleys where crust is born, great fractures where plates slide past each other, trenches where one plate descends beneath another. The former sea floor would not be a permanent frozen snapshot. It would weather, slump, fracture, erode, and in tectonically active zones continue changing. Rainfall would be weaker overall, but wind erosion, thermal stress, occasional floods from remaining rivers, landslides, and volcanic activity would all begin reshaping the new landscapes. Over long spans, a dry Earth would develop its own second-generation geography, no longer merely the revealed floor of vanished seas, but the weathered, open surface of a different planet. The chemistry of the atmosphere would also begin to diverge from the familiar world in deeper ways. The ocean today is a major reservoir in the global carbon cycle, absorbing carbon dioxide, exchanging it with the atmosphere, storing dissolved inorganic carbon, and participating in the formation of sediments that lock carbon away over geologic time. Remove that liquid reservoir, and one of the planet's largest active partners in carbon regulation disappears from the surface system. The exact trajectory of atmospheric composition in such an extreme scenario would depend on many interacting processes: rock weathering, biological collapse, vegetation shifts, volcanic degassing, soil carbon release, and the altered behavior of carbonate-rich sediments.
What matters most here is not a precise forecast, but a structural truth. A dry Earth would no longer regulate carbon in the way an ocean Earth does. The same is true of oxygen in its broader ecological sense. The atmosphere would not lose its oxygen overnight because marine photosynthesis stops. Atmospheric oxygen is vast compared with annual biological turnover, and both terrestrial plants and remaining aquatic systems would still contribute for a time. But the long-term balance between oxygen production and consumption would be altered because marine phytoplankton contribute a large share of global photosynthesis. Once again, the point is not sudden atmospheric collapse. It is the slow removal of a major planetary function. The disappearance of the oceans would reveal how many of Earth's balances are not guaranteed states, but maintained relationships. Could the oceans ever return? The question emerges naturally from the emptiness, and the answer is not simple enough for comfort. Earth holds water in many places besides the sea, in glaciers, lakes, aquifers, minerals, sediments, the atmosphere, living tissue, and even within the mantle and crust where water is bound into rocks or released through geologic processes. Volcanic degassing over immense spans of time can bring water vapor from the interior to the surface. Chemical weathering and tectonics can move water between reservoirs. In that sense, Earth is not a planet that knows only one place for water.
But a scattered and hidden hydrosphere is not the same as a restored global ocean. If all surface oceans disappeared, a future return to true oceanic abundance would likely require timescales far beyond any human horizon. And even then, the path would be uncertain. Small inland seas or regional water bodies might form earlier where topography, climate, and runoff allowed. Some basins could collect water from surviving rivers or melting ice. Certain low areas of the former seabed might hold lakes or briny inland seas if inflow exceeded evaporation locally. But the recreation of something like the modern world ocean would demand not just water in places, but enough available water at the surface under the right temperatures and pressures to fill the largest basins again. That is a different proposition altogether. This thought alone changes how the earlier parts of the story feel. The oceans are easy to treat as permanent because they look permanent within a human life. They outlast storms, empires, technologies, and languages. Yet, from the perspective of the planet, even they are a condition, not a law. Their presence depends on deep balances of temperature, pressure, chemistry, gravity, tectonics, and long geologic history. To imagine them gone is therefore to discover something unexpectedly moving about the real world. The sea is not just big, it is contingent. It did not have to take exactly the form it did, and if it had not, everything from weather to evolution to civilization would have unfolded differently. A dry Earth would in some ways resemble the worlds we already see elsewhere, but only in partial and revealing ways. Mars is dry at the surface today and bears strong evidence of ancient water. Channels, deltas, minerals formed in water, polar ice, and a landscape shaped by a hydrological past. Yet Earth without oceans would not simply become Mars. It would still have stronger gravity, a thicker atmosphere, at least initially, active tectonics, larger remaining water stores in ice and groundwater, and a far richer biological inheritance. At the same time, it would move closer to something Martian in one profound respect. It would become a planet whose surface openly remembers water more than it expresses water. Its geography would become an archive. That comparison is useful because it reveals what oceans truly do for a world.
They are not just a place where life happens to live. They are agents that soften, conceal, transport, dissolve, buffer, and connect. They hide tectonic architecture beneath a moving skin. They keep climates from swinging too far. They make clouds common. They let rivers finish their journeys. They allow currents to carry heat and nutrients around the globe. They create habitats from sunlit shallows to lightless depths. A world without oceans is therefore not simply a world missing water. It is a world missing one of the main ways complexity is held together at scale. From the perspective of evolution, that realization is especially powerful. Life on Earth did not begin on dry continents under open sky. The oldest evidence points toward a living planet whose earliest chapters were aquatic. Over immense time, life moved through oceans, coasts, rivers, wetlands, and eventually onto land. Marine chemistry, coastal transitions, climatic moderation, and long cycles of carbon and nutrients all helped create the conditions in which complex organisms could arise and diversify. Even human beings, who often imagine themselves as creatures apart from the sea, are descendants of a world shaped at every stage by water. Our blood chemistry, our embryonic development, our dependence on weather, our trade, our food, our myths, and our migrations all carry traces of that inheritance. There would also be consequences for coastlines that survive only as fossils in the new geography. Modern cliffs, beaches, dunes, barrier islands, and estuaries are shaped by constant negotiation between waves, currents,
Sediment supply, and storms. Once the sea is gone, those forms stop being active landforms and become abandoned gestures. A beach without waves is simply sand awaiting wind. A barrier island without tides or storm surge becomes an oddly placed ridge. An estuary without salt water becomes a valley or marsh in retreat. Over time, many of the classic signs of the old coast would blur, while the much larger architecture of the exposed shelf and slope would begin dominating the eye. The world would slowly stop looking like a coastline deprived of water and start looking like a different planet with a mysterious past. This transformation would alter memory itself. Human cultures are deeply coastal, even when individuals live inland. Trade, language, empire, migration, religion, holidays, cuisines, and literature have all been shaped by the sea's presence as route, border, danger, and promise. A world without oceans would not just reorganize survival, it would reorganize imagination. Words like island, harbor, tide, reef, voyage, and horizon would survive, but increasingly as inherited concepts pointing toward a lost condition. Children born long after the disappearance might know the sea first as story, then as geology, then as the vast open basins beyond the old shelf edge. To them, a whale might sound as mythical as a dragon once did to us, a creature too large, too gentle, too impossible for the dry world they know. And still, evidence of the former ocean would remain everywhere. Marine shells would be found far above the new basins, where ancient seabeds had once been uplifted into mountains long before the final disappearance. Salt would collect in old depressions and inland basins like a chemical echo. The pattern of rocks on continents would still record repeated cycles of marine advance and retreat from earlier ages. In that sense, the end of the modern oceans would not erase Earth's water history. It would make that history easier to read, though far sadder to inhabit. Geology would become a book opened to the wrong page, one that explains the past while offering little comfort in the present. For scientists, this world would be both catastrophe and revelation. Oceanographers, climatologists, geochemists, paleontologists, and biologists would suddenly be able to examine in direct detail terrains and transitions they had previously known through sonar, drilling cores, remote instruments, and rare submersible visits. The continental shelves would display old river systems drowned by rising post-glacial seas. Deep basins would reveal sediment patterns that tracked currents no longer moving. Ridge systems would show crustal youth and faulting with shocking clarity. Yet that knowledge would arrive in the middle of collapse. Every discovery would be shadowed by the fact that the living systems once associated with those structures had already been destroyed. The planet would become more legible precisely as it became less habitable. Perhaps the most profound scientific lesson would concern scale. On the modern Earth, it is easy to think in layers: climate in the sky, geology in the ground, biology in living things, history in human records. The dry Earth would dissolve those separations. A vanished ocean would turn marine topography into climate history, climate change into food crisis into migration, migration into political geography, and political geography into new evolutionary pressure. It would demonstrate in the starkest possible way that Earth is not a stack of subjects, but a single interacting system viewed from different angles. The sea had always been one of the strongest links between those angles. Its disappearance would make the unity of the system impossible to ignore, and for anyone simply standing under the altered sky without instruments or models, the lesson would be simpler. The world would feel less connected. Rain would no longer seem to come from nowhere.
Rivers would no longer seem eternal. Cool coasts, soft marine air, and clouds gathered over far water would be understood at last as expressions of one giant hidden partnership. The sea had not merely occupied space between continents. It had tied distant conditions together so completely that, while it remained, most of those ties were invisible. And perhaps that is the final softness hidden inside the question. Imagining the Earth without oceans does not only show us loss, it also restores a kind of attention. It lets the real planet return to view not as scenery, but as process. The sea outside a window, on a map, from an aircraft, from orbit, or at the end of a river is easy to call obvious because it is so large. But what is obvious is often what goes unexamined. By taking it away in thought, we make room to see it again and to feel, perhaps more deeply than before, that the blue of Earth was never merely a color. Now the world grows quieter. The last rivers run where they still can. The last clouds drift over mountains and pale basin floors. Far out across the exposed shelves, night settles into the scars and ridges of a hidden planet made visible too late. Somewhere in the dark, cold air moves over old seabeds, carrying traces of salt. Somewhere else, deep beneath stone, water still waits in silence. And above it all, the earth continues, vast, patient, and strange, holding in its dry basins the memory of an ocean that once made the whole world breathe. So let the image remain there for a while. A planet still turning, still lit by a distant sun, still wearing its continents and clouds, but no longer blue in the way we knew. The shelves lie open, the trenches descend into shadow, the ports overlook emptiness, the mountains keep their snow a little longer,
A river threads through a cooling valley toward a basin that will never return its water as sea. And in that long, thinning dusk, the absence of the oceans becomes one final kind of presence.
Quiet enough to drift with, wide enough to disappear into, and still enough to follow all the way into sleep.